Hello students, welcome you all. In pericyclic reaction, today I will explain 1,3-dipolar cycloaddition reaction. So this 1,3-dipolar cycloaddition reaction is an example of 4+2 cycloaddition reaction which takes place under thermal condition similar to that of Diels-Sade reaction. So Diels-Sade reaction, that was also 4+2 cycloaddition reaction, and that undergo under this thermal condition. So in Diels-Sade reaction, what we saw, one component was diene and another component was dienophile. Now here, the one component is 1,3-dipolar species and the other component, that is is dipolarophile. Okay, so this 1,3-dipolar cycloaddition reaction, one of the main thing, it is an example of 4+2 cycloaddition reaction. This is an example of 4+2 cycloaddition reaction, takes place under thermal condition. And here one component is one 3-dipolar species. And this 1,3-dipolar species, it must contain, it contains at least one heteroatom. Okay, containing at least heteroatom. For example, if you see in a general way, suppose if A, this is 1,3-dipolar species, and this is maybe written in a 1,3-dipolar form as A. Okay, so this must contain, this 1,3-dipolar species, it must contain one of the heteroatom. And other component is called as dipolarophile. And this is similar to dienophile, and for example, it may be this double bond species or it may be triple bond species, like this. Okay, now, so here suppose if we have this 1,3-dipole, then it can interact with a dipolarophile and to interact, and this will give you what kind of interaction will take place under thermal condition. 4s plus 2s interaction, that is superficial interaction takes place as per the selection rule. If the system contains the 6 electrons, then it will undergo superficial interaction, and it will give 5-membered this ring system. 5-membered heterocyclic compound is formed. In the same way, suppose if we have a suppose if we have such kind of so this may be what this is another 1,3-dipolar species, and it may combine with dipolarophile and it will undergo 4+2 cycloaddition reaction, that is 4s plus 2s superficial interaction, and you will get a 5-membered heterocyclic compound like this. Okay, so one of the application of this cycloaddition reaction to synthesize, it is used to synthesize heterocyclic or 5-membered heterocyclic compound. 5-membered heterocyclic compound. Okay, so let us take some of the examples of 1,3 dipolar species. So if I take some examples. Now, so one of the things that I should mention here, the orbital consideration, how this superficial interaction is possible. So if you see the orbital consideration here, then this 1,3 dipolar species, this is 3-atom species, as you can see, and I have already told you the molecular orbital diagram for this odd atom species. Now if this is 3-atom species, then it will contains the 3 molecular orbitals that can be denoted as psi1, psi2 and psi3. So means psi1, psi2, psi3, that would be the 3 molecular orbitals, and if you see, then it is having plus sign, and this psi2 having again this 3, and it is containing one node that pass through the carbon atom, as I have told for the allylic type of system. So one of the node that pass through the carbon atom, and this is containing, suppose it is containing plus minus, end orbital contains the plus and minus charge, and this psi3, this is the psi3, and that is plus minus plus, but it contains the 2 node over here. So these are the molecular orbitals for this 1,3 dipolar species, psi1, psi2, psi3. And dipolar file, it contains the 2 molecular orbital similar to the alkene type of system. Either you may write pi1 and pi2, or pi1 or pi star. So now here, either this may act as a HOMO, this may act as a LUMO, or vice versa, it may act as a LUMO or this may act as a HOMO. Suppose I take this one as a HOMO. Suppose if I take the HOMO of this dipolarified, so 1,3 dipolar species. Now suppose HOMO is of 1,3 dipolar species. Okay, then HOMO for this, that would be, because this is a 4-electron species, as this is a 4-electron species, this is 2-electron species. So here this would be the HOMO would be psi2 would be the HOMO, highest occupied molecular orbital, that is containing here 2 electrons, 4 electrons are filled up, and this psi2 would be the HOMO. So now I may write the HOMO, that is psi2 would be the HOMO, and it is containing plus sign, and this is containing the minus sign. Okay, now so LUMO, next one is the LUMO, that is for this dipolarified LUMO. So that is dipolarified is the LUMO, and suppose this this is pi star. So pi star is the LUMO over here, and that is plus sign and minus sign. Okay, now because this is a HOMO, then no doubt it will act as an electron rich component. This is electron rich component, and this is electron deficient component in this case. Now here, as you can see, the interaction superficial interaction is positive, is possible, and we are getting the 2 bonding interactions here. And here, because this is electron deficient species, then if the 1,3 dipolar species act as a HOMO and this act as a LUMO, then must contain some of the electron withdrawing group. So one of the electron withdrawing group that may be present, suppose this is the electron withdrawing group which may be present over here. So in dipolarophile, in this case the dipolarophile must contain some electron withdrawing group. Now second case, when this 1,3 dipole acts as a LUMO. Suppose 1,3 dipole, it acts as a LUMO, and suppose for LUMO means psi3 will be the LUMO. So psi3, I may draw the psi3. This is our psi3, means positive, and the lobe is having the positive sign. Two nodes are present over here. Okay, so this is our psi3, and this is electron deficient in this case. This acts as electron deficient, whereas HOMO, that is for dipolarophile HOMO, and that is pi, and this will act as here electron rich part. So means positive, and sorry, this is our HOMO. Yes, this is positive and positive. So again you will see superficial interaction is possible over here. So as this is electron rich, that's why it must contain some of the electron donating, electron releasing group over here. So if it contains electron releasing or electron donating group over here, then it will act as a HOMO, and this will act as a LUMO. Okay, so in this way we can understand the how the superficial interaction is possible over here. Now let us see some of the examples. Now if you will see some examples. Now before coming to the example, let us give you some of the examples of 1,3 dipolar species. Okay, so examples of 1,3 dipolar species. Now, for example, this ozone here, it may act as a 1,3 dipolar species, and here it is having the positive sign, this is having the negative sign, and or it may be written in a resonance stabilized form, and here this is having positive sign, this is having negative sign, like this. Or suppose azide, alkyl azide, maybe this is our alkyl azide, and this, that is azide, and here that may be written as a 1,3 dipolar species, and positive sign over here, this is negative sign. Or diazomethane. Now suppose we have okay, so this is our diazomethane, and it may be written as a 1,3 dipolar species. Positive over here, negative over here. In the same way, suppose if we have examples like oxiranes. From oxiranes we may form the okay. So positive charge is coming over oxygen, and double bond over here, and negative charge over this carbon. Now this in 1,3 dipolar species, so like this. Now here positive charge, and here one of the negative charge, like this. So this is the another for oxidants, and in the same way, you suppose if you have azirenes, here, this bond 3-membered ring, it will break. Under thermal condition it may break, and what you will get here, you will get positive charge over this carbon double bond, and here this bond has broken down, so you will have the negative charge like this. So this may be written like this, and you will get, sorry, so this is like this, and or from nitrile or from nitrile also we may see, suppose if we have a nitrile, oxide of nitrile, that also gives the nitrile oxide, we may write it as a nitrile oxide, and what it will give you, it will give you the 1,3 dipolar species. Okay, now come to this nitrons. This is our nitron. Okay. This is nitron, and some other examples like yes, ylide of this oxygen ylide. If you see this oxygen ylide, okay. So these are different 1,3 dipolar species, and you may, with the help of this, you may understand some of the reactions. Now let us see a few reactions. Now suppose we have one dipolariphile, and in presence of this ozone under heating, 4 plus, that is 4s plus 2s cycloaddition reaction, and the product that you will get after this one, this would be the product in this case, because it can be written as this one, this can be written this, it will give the 1,3 dipole ozone, and we may write like this. In the same way, suppose if we have the another one, and suppose like this phenylazide, if I write this phenylazide, then we may write okay, so this positive charge over here, negative charge over here, and this will also give under thermal condition again 4s plus 2s cycloaddition reaction, and you will get the this one. Okay, now yes, so this would be the product in this case, and one of the phenyl group is present over here. Now in the same way, you may see some, suppose this one, and this may some diazomethane type of okay. Okay, so and this may also be, if suppose one of the hydrogen is present over here, and this may give you this may be written like this. Okay, so here double bond over this one, single bond, and here nitrogen and H2. Okay, so now, so let us see, suppose if we have next example, if you see, now what should be the product if we have this one. Now what should be the product in this case? So here in first step, one of the 1,3 dipole species that would be formed. So in presence of triethylamine being a base, it will take this proton, and we have negative charge over here, and what we may write, and here negative charge over this one, and in next step we may leave this chlorine, may leave, and so positive charge and this one negative charge like this. Okay, so here in next step it will give the minus, and this will be plus. Now this will be formed. Okay, so here we are getting the 5-membered heterocyclic ring is formed. 5-membered heterocyclic ring is formed, and this is one of the product which is possible. Now this may add, this dipolar may add in another way, and in that case the other product which is possible, the next product possible, that would be the final product. So this here you can see these 2 phenyl rings are far away from each other, and here the 2 phenyl rings are cis, you can say cis to each other. So this would be the minor product, and due to the sterically hindered product, this is the major product, this would be the main product like this. Okay. Now another example. Now what would be the product in this case? Now what should be the product here? Now in first step, so this will, in presence of triethylamine, this is going to give one of the 1,3 dipolar species, so hydrogen. So this is electron withdrawing group is present on this carbon. So this carbon, that is the acidic hydrogen over here. One of the acidic hydrogen is present over here, and what you may find here, one of this group that is minus charge, and in next step, or that may be written like this. So here this nitro group, this is our nitro group, and minus charge over here. In next step, this will go over here, this is here. So what you may write? You may write double bond and nitrogen, positive charge, negative one here, another negative one here, like this. Okay, now again we have this triethylamine containing this So this triethylamine having this hydrogen, so it will take here this proton, and we have this one nitrogen over here and oxygen and this OH. Okay, now here so triple bond over here, we have triple bond, yes, okay. This positive charge, again we have the positive charges present on this nitrogen. Okay, now so positive charge over here, and now this one is having a negative charge like this. So this is the 1,3 dipolar species which is formed, and in next step this will add with one of the dipolarophile. So this is our dipolarophile 2 plus this addition will takes place, and the product formed, this would be the product formed over here. Okay. So because this is a superficial addition, so in product the stereochemistry for this one that will remain same here. This is cis alkene, so here also the two groups that would remain, two methyl group will remain in the same position. So these are some examples for the 1,3 dipolar cycloaddition reaction. Thank you.